Sometimes, the simplest observations can lead to the most profound questions in science. The planets and stars, those twinkling lights above, are not vast distances away as mainstream science claims. As you look at the night sky, on a clear night, you see an abundance of lights, with different colors and brightness. The inverse square law of light, along with the limitations of the human eye, control all we can see. We can see Mars' reddish-orange color with the naked eye. However, human eyes need at least 0.01 lux of light to perceive color. This simple fact challenges our conventional understanding of Mars' distance and size. If Mars is far away as commonly believed, it will not provide enough light for us to see its color. Yet we do. This observation doesn't align with traditional measurements of Mars' orbit. We see the color of planets and many objects in the night sky. Given that human color vision requires at least 0.01 lux, this observation has profound implications for our understanding of the night sky. If these celestial bodies are providing enough light for color perception, they must be significantly closer than conventionally believed. This simple yet crucial observation tells us, we need to fundamentally re-evaluate our understanding of astronomical distances, object sizes, and the structure of our cosmic neighborhood. This expanded perspective shows us, we need to reconsider the entire model of the cosmos. The Moon reflects, on average, 15,600 lux of the Sun's light. From the full Moon, our eyes receive approximately 0.5 lux. If the Moon was 130 times further away, it would not be visible. We are told Mars is 139 to 750 times further away. Mars reflects less light than the Moon. But we see its light and color. At those distances, this would not be possible. The brightest star in the night sky, Sirius. It would be 25 times brighter than the Sun at the same distance. At 8.6 light-years away, seeing its blue-white glow would be impossible. It would not be visible. At their stated distances, seeing the color of planets and stars is a massive problem. None of them would send our eyes the required level of light to perceive color. Telescopes just intensify the problem. As they magnify, they reduce the level of light to the individual rods and cones of our eye. Part 2 in this series of short videos is about the inverse square law of light. Part 3. How our eyes see and perceive light. Part 4. The impossibility of seeing planets at their stated distances. Part 5. Impossible stars. Then Part 6. Telescopes and light. How a telescope makes objects less bright as they magnify. Lux is Latin for light. This is a measure of the intensity of light, as perceived by the human eye. 1 lux is based on the amount of light a plumber's candle illuminates a 1 meter square surface, placed 1 meter away. We use a lux meter to measure the level of light. A lux meter mimics human vision in 2 key ways. Its sensor matches our eye's light sensitivity, peaking at green and yellow. Its lens captures a similar field of view to human peripheral vision. This dual approach lets it measure light in the same way we perceive it. At 1 meter, the reading is 1 lux. From this information, we can work out what the readings will be at any distance. Place your lux reading from 1 meter away at the top. Then the distance required. 2 meters. Square the distance. 2 squared is 2 times 2. 1 divided by 4 is 0.25. The lux reading at 2 meters will be 0.25 lux. What will the reading be at 10 meters? Square the distance. At 10 meters the reading will be 0.01 lux. All light travels in this mathematically predictable way. It's a law of physics. The inverse squared law, for light. Let's let Professor Eric Rogers explain the inverse square law with his famous butter gun.
That with a fable. Suppose a restaurant has the problem of buttering toast and wants to be very modern and do it with a machine. So the proprietor invents a butter gun with melted butter in here, which can be squirted out in straight line spray of butter like that. Here's the piece of toast, and lines of butter go out and hit it there, and there, and there, and there, and butter it all over. Now instead of that, lines might go on, and you could put the toast further back at twice the distance, 2 pieces of toast wide, 2 toasts high, and altogether you would put 4 pieces of toast there to intercept the butter, and you'd be half as thick, no, quarter as thick buttering. Inverse square law. At 3 times the distance, 3 pieces of toast, 3 pieces of toast, altogether 9 pieces of toast, and you would get 1/9 of the buttering economy treatment.
The first toast at 1 meter has 36 butters, or 36 lux of light. At 2 meters, the 36 lux or butter is spread over 4 square meters. The meter reads just 1 square meter of that area. This continues. At 6 meters your meter will read 1 lux. As the light at 1 meter is now spread over 36 meters squared. Light is extremely good at speed. But it's not that good at keeping bright over distance. From 1 to 2 meters the brightness falls to a quarter. At 10 meters 1/100th. On a moonless dark night, for a human to see a light source, at least 0.0001 lux of its light must reach the eyes. Below that, it will be invisible. Criquet Lighthouse in France is considered the most powerful lighthouse in the world. From 1 meter of the light, it would measure an incredible 500 million lux. It has a range on a clear day of 69.5 kilometers or 43.2 miles. As powerful as it is, at 10 kilometers, the lux reading from the light would only be 5 lux. At 69.5 kilometers, the reading will be 0.10351 lux. Allowing for a small loss due to the atmosphere, it will soon be below the visible limit. We have confirmed the lighthouse range using the inverse square law for light. On a moonless dark night, for a human to see a light source, at least 0.0001 lux of its light must reach the eyes. Below that, it will be invisible. Let's move on to color. To see the color red, white light, made of all the colors of the rainbow, each with their own wavelength, hit the object. All colors are absorbed, other than red. It's the same for any color we see. Your eye has three types of cones that respond to color: a red, green, and blue cone. From the information they gather, we see over 10 million different colors. If the lux level from the object, or light source, falls below 0.01 lux, the color cone receptors become inactive. Rods, marked in gray, are responsible for vision at low light levels are activated. Then we only see shades of gray. Look at a red car, in low light, it will be gray. This is called scotopic vision. Peripheral vision. Hold your arm out to the side and wiggle your fingers. You can sense movement without looking at it directly. This is how our eyes detect very faint light, below 0.0001 lux. In near darkness, our peripheral vision, rich in light-sensitive rod cells, can detect faint light and motion. When we look directly at the source, it seems to vanish. That's because the center of our vision lacks these supersensitive cells. This is why we sometimes catch glimpses of faint stars or dim objects in the corner of our eye, then lose them when looking straight at them. 3 key points to remember. 1. If the light from an object or light source falls below 0.01 lux, you will not see its color. 2. On a dark moonless night, an object or light source will not be directly visible if the light hitting your eyes falls below 0.0001 lux. Third point. Only in your peripheral vision can your eyes detect light levels below 0.0001 lux. The inverse square law of light, along with the limitations of the human eye, control all we can see. As you look at the night sky, on a clear night, you see an abundance of lights, with different colors and brightness. Light travels from the sun to each planet. Some of that light is reflected. It then travels over vast distances to Earth and your eye. Under ideal dark sky conditions, the furthest planet you can see, with the unaided eye, is the planet Uranus. It has a slight bluish or greenish hue. It's over 2,586,000,000 kilometers from Earth. The Sun's light must travel over 2,872,000,000 kilometers to this planet. Then reflect from the surface, travel back to Earth, meeting the light requirements of your eyes to be able to see it. Is that possible? Our moon is stated to be about 400,000 kilometers away. On the moon, direct sunlight measures 130,000 lux. On average, it reflects 12% of that light. At 12%, the light reflected is 15,600 lux. From Earth, the light received from the moon is 0.3 to 0.5 lux. If the moon was 130 times further, it would not be visible to the naked eye. The moon will be our reference. Earth receives 130,000 lux from the Sun. Given the distances of each planet, we can use the inverse square law to calculate the lux level the other planets receive. We will set Mars as reflecting 25% of visible light. All the others we set to 55. This is the amount of visible light reflected from each planet back to Earth. This is the distance it must travel to Earth, meet the requirements of your eyes, for you to see them in color, or see them at all. Uranus. The books state 49% of the light is reflected. At 55%, it is reflecting about 200 lux. To use the inverse square law for light, our first measurement should be at a distance of 10 times the diameter of the planet. Its angular size will then be about 6 degrees. In reality, the planet would be below 0.5 lux at this distance. For now, we will vastly overestimate the reading at this distance at 50 lux. Uranus to Earth distance. We can now use the onboard calculator to calculate the amount of light reaching Earth. Lux and the distance at the top. Distance between planets. With no allowance for a reduction due to the atmosphere, this is the level of visible light arriving on Earth and your eyes. With the naked eye, or even an optical telescope, your eyes would not have enough light to see anything. Yet we do. The planet Mars. Mars at its closest is 55,650,000 kilometers away from Earth. At its furthest it's 300 million kilometers. With the naked eye, we can see its light and color. Mars at its closest is over 139 times further than the Moon. At its furthest, 750 times. At Mars's stated distances, it would not be visible, let alone visible in color. It reflects less light than the Moon, and is over 139 times further away. To put this in context, a framed image of Mars with just the moonlight illuminating it. You have 1,000 times more light hitting your eye from this image, yet see no color. None of the planets would be visible. Mars, Jupiter, Saturn, Uranus, and Neptune would not send your eyes enough light to see them in color, or see them at all. They all reflect less light than the Moon. The only explanation there can be, with the color and lights we see, is that the planets are a lot closer than we're told. We are told the Sun is about 150 million kilometers away from Earth. Or 1 astronomical unit, AU for short. At my latitude, the reading for direct sunlight is 100,000 lux. How far would it need to be to not be visible? Be below 0.0001 lux of its light, hitting my eye. The answer is 31,623 times further. 0.5 light years. What if the Sun was 10, 100, or 1,000 times brighter? At 10 times the brightness, 1 million lux on Earth, it would not be visible at 100,000 AU, 1.58 light years. 100 times the brightness, 10 million lux on Earth, not seen at 316,228 AU or 5 light years. And at 1,000 times the brightness, 100 million lux on Earth, invisible at 1 million astronomical units. That's 15.8 light years away. Any star 10 times the brightness of the Sun or less would not be visible if it's over 1.5 light-years away from Earth. A star at 100 times brighter than our Sun is not visible at over 5 light-years away. And any star 1,000 times brighter than the Sun or less will not be visible if over 15.8 light-years away from Earth. Absolute and apparent magnitude are the two ways to measure a star's brightness. The apparent magnitude is how bright a star looks viewing the night sky from Earth. Then absolute magnitude, this is how bright stars including the Sun would appear at a standard distance of 32.6 light-years away. The lower the number, the brighter the star. Sirius at a distance of 8.6 light-years is the brightest star in our night sky. Its absolute magnitude is plus 1.43, which means it's about 25 times brighter than our Sun. Vega, the fifth brightest star. It's a blue-white star, located approximately 25 light-years from Earth, with its absolute magnitude of 0.58 making it about 50 times brighter than the Sun. Vega and Sirius would not be visible. At 1,000 times and 100 times the Sun still would not be visible. HD 140283, also known as Methuselah's star, located about 190 light-years away. At an absolute magnitude of plus 3.377, is only 4 times brighter than the Sun. Yet using low-powered binoculars, you can see its light. That's not possible. How is it that looking through a telescope, you see thousands more stars than with just the naked eye? There are two possible answers. 1. As commonly believed, the additional stars are light-years away. At their great distances, the light from the stars is not at a sufficient level for our eye to see. A telescope can only make the additional stars visible by increasing the level of light to the individual rods and cones of our eye. Magnification will make very little difference, as their angular size is extremely small. 2. The stars are closer and smaller. Their angular size is too small for our eyes to resolve. With magnification, their angular size increases and makes them visible. Can this telescope make a star that's 6 times too dim or more visible? There are two types of telescopes, a refractor that uses a lens to gather light, and a reflector scope that uses a mirror. The light-gathering power of a scope is determined by the diameter of this objective lens, compared to the pupil of the human eye, at 7 mm. A 130 mm lens, divided by 7 mm, then squared, gives us a light-gathering power of 345 times more than our eye. Magnification is the fixed focal length of the scope, divided by the focal length of the interchangeable eyepiece. The Astro Master 130 EQ has a focal length of 650 mm. With the 10 mm focal length eyepiece, it's 65 times magnification. With the 20 mm, it will be 32.5 times. Looking through a telescope, a usable image is a balance of the light-gathering power of the telescope and the amount of magnification used. A dim object with a small angular size takes up a small area of the retina. If we magnify the object without increasing the amount of light, the angular size will increase, The individual rods and cones receive less light, so the image will be larger but dimmer. With the additional light being gathered by the main lens, it becomes brighter, with 345 times the light gathering power of the eye. Magnifying the object 18.5 times will get the equivalent brightness as the naked eye. Each of the rods and cones will receive the same amount of light. This is because the light is projected over 345 times the area, equaling the 345 times light that is gathered. Increasing magnification beyond 18.5 times reduces the amount of light hitting the rods and cones, creating a dimmer but larger image. The only way to make a very dim object brighter is to reduce the magnification below 18.5 times. This increases the light level to the individual rods and cones of our eye, creating a smaller but brighter image. The torchlight represents the light from the distant object, amplified 345 times. When projected onto the wall or retina of our eye, the area of the light is equivalent to 345 times in area than the light in the distance. Both lights are the same brightness, one is larger, as it would be when magnified onto your retina. With greater magnification, the available light covers a larger area, getting dimmer the more you magnify. The only way to make a dim object visible is to magnify below the equal brightness threshold. The problem is, with a standard size eyepiece, no telescopes do this. For different aperture sizes, the equal brightness magnification is simply the square root of the light gathering power. To be visible, this star needs to be 6 times brighter. Using this telescope, at 18.6 times magnification, we have equal light to the individual rods and cones of the eye. There is no increase in brightness, yet we see more stars. Using the 20mm eyepiece with 32.5 times magnification, the light becomes dimmer. And at 65 times magnification, the light to the rods and cones of our eye is 12 times dimmer. Using a telescope with 345 times more light gathering power than your eye lets you magnify an image 18.6 times without losing brightness. But here's the catch. If you magnify beyond 18.6 times, stars start to dim. A star just bright enough to see at 18.6 times magnification will fade from view at higher powers. Beyond this, the telescope is only magnifying, it's not making things brighter. Importantly, a star that's 6 times too dim to see with the naked eye will remain invisible. Yet we see more celestial objects, including colors. As you move away from this 500 million lux lighthouse, the light dims according to the inverse square law of light. When its light just becomes invisible to the human eye, it would be impossible for this telescope to make it visible. The stars must be closer and smaller. What's the evidence that the planets are a lot closer than we're told? We first need to understand the limitations of our eyes. The cones of our eye need at least 0.01 lux of light to see color. This goes for any large or extremely small colored object or light. This is well documented in many experiments and papers. At the planet's stated distances from the Sun, we can use the inverse square law to work out the amount of light each of the planets will receive. Given the percentage of light each planet reflects, their distance from Earth, and the radius of each planet, we can work out how much of their reflected light reaches Earth and our eyes. We are using GeoGebra to input the math and numbers to produce an interactive calculator. Let's start with Mars. At its stated distance, this is the amount of light hitting the Earth's outer atmosphere. We then have an additional loss of light as it passes through the atmosphere to your eyes. The lux level would need to be over 200 times greater for you to perceive the faintest hint of color. It's well below the level of light needed to even see it. As we look at each planet in turn, they get further from the Sun and Earth. Thus the amount of light reflected back to Earth gets lower and lower. None hit the light requirements to be able to see them directly. Our Moon. Given the Moon's distance, its radius, and the amount of the Sun's light a full moon reflects, the calculation for the amount of its light hitting your eye on Earth is reasonably accurate. However, it's also accurate with the Moon being smaller and closer. Telescopes. Telescopes making the light brighter to our eye seems to be greatly misunderstood. Due to the optics, they all have a loss of light. In some cases this is over 30%. Yes, they do collect more light, but there are limitations to how much you can magnify. Here are 3 different aperture sizes with their light gathering power. The square root of the light gathering power gives you the maximum magnification to get equal brightness with a larger image. Anything above this is reducing the level of light to the rods and cones of our eye. Equal brightness magnification is when a telescope's image appears as bright as what you'd see with your naked eye. Your eye's rods and cones receive the same amount of light as they would without the telescope, but see a larger image. Higher magnification spread light over more rods and cones, so each gets less light. Telescopes actually prove planets are close. A case in point, Neptune. Neptune, at 30 times further away from the Sun as Earth, receives only 144.5 lux of light from the Sun. It reflects only 79.5 lux of that light. It then needs to travel 29 AU, or Sun-to-Earth distances to our eyes. This is the amount of light hitting Earth. To directly see Neptune, the light needs to be over 38,000 times greater. To see its blue color, nearly 4 million times. Neptune is not visible with the naked eye, you need a telescope. The Backyard Astronomer's Guide recommends around 100 times or more magnification to see Neptune and its color. The problem is, this will be well above the equal brightness magnification. The light from Neptune will be 33 times less than with the naked eye. The light gathering power of a telescope only helps if Neptune is closer and smaller. Its angular size is too small for our eyes to resolve. Using a telescope with 108 times magnification gives a larger angular size and makes it visible. Our eyes need 0.01 lux of light to see the faintest hint of color. 2. They need 0.0001 lux to directly see a light or object. 3. The planets at the distance mainstream science states don't send our eyes anywhere near the levels needed. 4. Telescopes don't increase the lux level to the rods and cones of our eye. They reduce the level, a greater reduction of light, with greater magnification. 5. If telescopes don't increase the level of light to rods and cones, stars cannot be too dim to see, they must be too small to see. And 6. Telescopes' magnification alone makes more planets and stars visible. Thus they must be closer and smaller.